Hey, good morning, everyone. Today is day 4, where I trade every day, one try hack me room, one new skill, always ethical, and by 30, I'll be a professional hacker. I actually started recording this video earlier, and then I noticed halfway through the microphone wasn't picking up my audio. Luckily, I did not get that far, but I'm going to just pull up what I've done so far. I've enumerated all of the ports, and this is a Windows machine, and we discovered that SMB is available on this machine, as well as a port called 31337. So here, we're going to just analyze our findings really quick. This is an incredibly hard room, um, and it's going to be here. Let's review our findings here. So I'm just gonna write an nmap scan, and nmap the nmappers revealed ports 135, 139, and 445 open. These right here are the SMB ports. It looks like RDP is on this machine. This is on a work group. It's not part of a domain. As we can see here, Gatekeeper. And we have this port right here, 31337. After digging around to figure out what is this port 31337, we discovered that what is port 31337? We figured out it is most famously associated with the malicious backdoor program Black Orifice. It has legitimate uses, but it's been flagged as a security risk. So clearly, this port is going to be very important in breaking into this room. Um, let's see, what else did we find? We also found some 49,000 ports. I didn't dig too deep into that. Once I saw this port, um, I kind of didn't look through this. Now, that's not probably best practice. I probably should look at see what these ports are. Let me just see. Microsoft RPC. What did I just do? I just pressed the wrong. I'm gonna keep going here. So we also saw that SMB was discovered. So Nmap runs SMB scripts as part of its default scan -sc. So it discovered the OS, which is Windows 7 Professional, very outdated. I'm sure I could find multiple vulnerabilities, but we're going to focus on what the room wants. Um, looks like we use the guest account to enumerate this. It didn't discover any shares. So I think let's enumerate the shares and see what we find. So I have several commands that I could use to enumerate SMB. First one I'm going to use is enum for Linux, and the IP address. And this is enumerating. It's using SMB to enumerate with whatever the default. If normally it's for anonymous, if you have an anonymous account, we may have found some user accounts. This kind of looks like defaults. Didn't really detect anything of value, it looks like. SMB client. We're going to not use authentication. We're going to list out the shares. And we're going to type in the IP address. And from this, we can find that we have a user's share available. I'm going to try to connect to it to 10.2.1.1.5 users. And I connected to it without any authentication. So if we list out the files in this share, we see default desktop.ini and share. We're going to go into the share directory and we find gatekeeper.exe. And this is where I left off at before I realized the microphone was muted. So, gatekeeper.exe. I believe that is associated with the port 31337. So let's take a look at what port 31337 is doing. So let's get out of here. I'm going to connect over to port 31337. 10.1.2.1.5.4. I'm doing 3133. Did I say 07 or 31337? So now I'm connected to this port on this machine. So, what does it do? It appears to just echo back anything that I type to it. And after reading a walkthrough, we find out that there is a buffer overflow once you exceed a certain amount of characters. It can't handle all of the text. So I'm going to try to replicate it real quick to see if I can get it to happen. And this guy, he used quite a lot of characters, so I don't exactly know what the buffer overflow is, or what the buffer overflow limit is. Is it this? I think that was it. I think it just buffer overflowed. So the objective is to use this exe file that we found, gatekeeper.exe, and we need to somehow manipulate this. Now this is insane to me. I've never done anything like this. This is actually the first time I've tried to exploit a Windows machine. So we got some challenges up ahead. The first challenge is, let's see. The first challenge is we need to analyze the gatekeeper.exe with an application known as Immunity Debugger. Simple enough, right? Except Immunity Debugger hasn't been in production for 12 years. So I have to find a way to install this. And I don't even know where to begin. This is Immunity Debugger is meant for Windows as well. So when we visit the Immunity Debugger page, I get a 404 error, which is fantastic. Fantastic. Oh boy, it needs Python and... Okay. How do we figure this out? It's not even loading. How do I get this? No chance this is loading. Nope. I'm sure there's multitudes of debugging programs I could use, but in this walkthrough it specifies Immunity Debugger. Now, I don't know if this... It's always good to see this. Is it trusted? I have no idea. So we're gonna just download it without without even checking, because I don't have any other options to download this. If you guys know how I could possibly verify if this is safe, that'd be great. I'm gonna run a virus total on it just to see if I could detect anything. Am I using my own computer right now? Oof, I'm using my own computer. Nope, nope, nope. Did not want to use my own computer. I want to use my virtual machine. Got a little confused there. Like, I can get that. Alright, we got that downloaded. We're gonna run it through virus total. Downloads. And I just want to see what this detects, if anything. Wonderful. Adware. Wonderful. Wonderful. Hmm. Um, that's the thing that sucks. I wish it did say adware. Okay, let's keep looking. This is gonna be the fun part. It's just trying to get this, and then afterwards it's even harder. But I guess that's the path I walk. I'm about to build this. Add another hour at this point. I wonder if that guy has. Can this run? For a Ford. Hmm. I'm gonna look up another walkthrough in hopes that this guy actually published a walkthrough. I'm going to. Um. Really? Let me do this. Maybe I'll be able to bypass the sign up requirement. Alright, bear with me one. Okay, we signed in. No. Okay, there we go. Okay, so this is the walkthrough. Wonderful. This walkthrough is not helping me at all. Okay, did that for no reason. Part of the process here. Okay, what is this room called? I think it's called Gatekeeper. Gatekeeper walkthrough. You got this wonderful person named Ahmed who made a. This is way. This is like insanely difficult. Let's try reflect cross out in my terminal or cross. Huh. Great, the connection is closed. That means this program in the server has been crashed. The next step is to get the binary versions. We did that. Let's do fuzzing to identify when the program will crash. Put big input in the program input like I did previously. First thing in buffer overflows, get the offset to know when the buffer will overflow. Then I'll generate the pattern 1000 byte by this command. Oh, so this generates a payload of 1000 bytes. Open the exploit script. I cannot believe this. How does this guy know this? All the chars we generated with the bad characters you didn't find. But it's so hard. Now let's go to use the second method. We'll use Mona module to find the bad char by this command. We'll find a jump point. This is incredibly hard. I think what I need to do. Buffer overflow. I was kind of just hoping there's a buffer overflow room. Buffer overflow. Because this is way too hard. Um, let's do this. Let's get my notes book out. Buffer overflow. No, whoops. Didn't want that there. No. Doo -doo. New buffer overflow. Didn't put that in the right spot either. Come on. Maybe I can just drag it right out here. Don't want it as a. Okay. Buffer overflow. Did that. Great. That's what I wanted. Okay. Start the machine. Connect to our network. When a program runs on a machine, the computer runs the program as a process. Current computer architecture allows multiple processes to be run concurrently at the same time by a computer. While these processes may appear to run at the same time, the computer actually switches between the processes very quickly. I did know that. Switching between processes is called a context switch. Didn't know that. Since each process may need different information to run the current instruction to execute, the operating system has to keep track of all of the information in the process. Okay. Higher memory address. Users. The memory in the process is organized sequentially. User stack, shared library regions, runtime heap, read write, read only. Okay. User stack contains the information required to run the program. This information would include the current program counter, saved registers, and more information. We will go into detail in the next section. The section after the user stack is unused memory, and it is used in case the stack grows downwards. Okay. Shared library regions are used to either statically or dynamically link libraries that are used by the program. The heap increases and decreases dynamically depending on whether a program dynamically assigns the memory. Notice there's a section that's unassigned above. I do see that. I see several sections. Above the heap, which is used in the event that the size of the heap increases, so it could expand. The program code and data stores the program executable and initialized variables. Where is dynamically allocated memory stored? Dynamically allocated memory stored in the heap? Where is information about functions, local arguments stored? The stack? Okay. Alright, so 86 and 64 procedures. And we've all seen 64-bit and 32-bit, so this must be where it derives from. A program would usually comprise of multiple functions, and there needs to be a way of tracking which function has been called, and which data is passed from one function to another. Makes sense. The stack is a region of contiguous memory addresses, and it is used. Let me just go look up what this word means. Sharing a common border. Okay. The stack is a region of contiguous memory addresses, okay, and it is used to make it easy to transfer control and data between functions. The top of the stack is at the lowest memory address, and the stack grows toward lower memory addresses. The top of the stack, that's key. Let me read that again. The stack is a region of contiguous memory addresses and is used to make it easy to transfer control and data between functions. The top of the stack is at the lowest memory address, and the stack grows towards lower memory addresses. Okay, so it goes upwards. The most common operations of the stack are pushing, used to add data onto the stack, and popping, which is removing. Okay. Push var. This is the assembly instructions to push a value onto the stack. It does the following. It uses var, or value stored in a memory location of var. Okay. Whatever the variable is. Let me just get a... I'll be honest, this is rather complex. But I figured buffer overflows and memory itself is complex. Decrements the stack pointer known as RSP by 8. Pop var. Now pop is when you remove, right? Am I correct? Use remove. Okay. This is an assembly instruction to read a value and pop it off the stack. It does the following. Reads the value at the address given by the stack pointer. It's important to note that the memory does not change when popping values of the stack. It is only the value of the stack pointer that changes. Each compiled program may include multiple functions, where each function would need to store local variables, arguments passed to the function, and more. To make this easy to manage, each function has its own separate stack frame, where each new stack frame is allocated when a function is called and deallocated when the function is complete. This is easily explained using an example. Look at the two functions. Int add, int a, int b, accepts two parameters. Int new equals a plus b, and you just return new. Okay? Int calc, int final equals add. Just calling the oh. Oh. So it's like nested. I see. Okay. So that makes sense. So int add would be like frame 1. This is like frame 2, and this is frame 3. I see. Okay. What direction does the stack grow? Use the symbol to represent lower and the symbol to represent higher. So it goes to the bottom, right? Right. You want me to type that? How am I wrong? No, did I type the wrong symbol? I thought that was the right symbol. Am I? What is going on? Unless that's an L, but I don't think that's an L. There was no way that was an L. No way that was an L. Anyway, what instructions used to add data onto the stack, and that's just push. Okay, the explanation assumes that the current point of execution is inside the calc function. In this case, calc is known as the caller function, and add is known as the callee function. The following presents the assembly code inside the calc function. For is this the memory that's allocated to each? I cannot believe this is the basics. This is like, I'm trying to figure out how can I understand this. The add function is invoked using the call operand in assembly. In this case, call q sim.add. Okay. The add function is invoked using the call operand. In this case, called. So he's running the script. Okay, so he's running that script we just saw. The call operand could either take a label as an argument, or it could take a memory address as an offset to the location of the start of the function in the form of call value. Once the add function is invoked, and after it is completed, the program would need to know what point to continue in the program. To do this, the computer pushes the address of the next instruction onto the stack. In this case, the address of the instruction on the line that contains moval %ex and goes down. After this, the program would allocate a stack frame for the new function. So call queue is gone and push call queue is gone. Now it's add. Oh my goodness. Once the function is finished executing, an instruction will pop the value of the return address of the stack. In the above example, we save the functions. We say that the function take arguments. The calc function takes 2 arguments, A and B, right? Up to 6 arguments for functions can be stored in the following registers. Oh. Okay. Jeez. What register stores the return address? I'm like amazed right now. I don't really know. RBX? Rax, like, Rax is caller saved. In the in the above programs, you can see that the binary information is represented in hexadecimal format. I do see that. Different architectures actually represent the same hexadecimal number in different ways, and this is what is referred to as NDNS. Let's take the value of 0x1 as an example. Here, the least significant value is the rightmost value, 78, while the most significant is the leftmost value. Little endian is where the value is arranged from least significant byte to most significant byte. Big endian is most significant to least significant. Here, each value you have to attach. Would you like to be so short? Um, Now that we've looked at all the background information, let's explore how the overflow actually works. If you take a look at the overflow one folder, oh right, I'm supposed to remote in. I'm actually a bit strapped for time. I'll be completing this room, but I just won't be completing it on camera. But this room will be completed. Um, yeah, this was a very hard one. As expected. I mean, I'm gonna be exploring some very difficult concepts as I move forward in this, and buffer overflow is definitely a significant one. Alright, thank you. I'll see you tomorrow.